about exergy, right? When we had our X destroyed. I'll be going fast with these slides because there's like 45 of them, right? So I can't really give all of them justice, but I want to at least review, especially these earlier ones. And please stop me if there's a question you have. But exergy destroyed, we had T naught S gen, right? And that has to be greater than or equal to 0. So it's irreversible process greater than 0, reversible 0. So there's 0 irreversible, at least S gen is 0, and it's reversible, right? And it's impossible to be negative, right? We had our exergy balance, where we had exergy entering, leaving, destroyed, and change inside our system. Okay, so we set it up that, and we had terms for heat. We had term for, work, right? And then the X destroyed and our change in exergy of our system. We had for a control volume or an open system, we see here, right? All right, so here's our closed system. We had here, and it's on our equation sheet too also, right? A nice summary of all the equations up on our equation sheet. And then we have our control volume, where you have the term for heat of exergy, the term for useful work. We have exergy being carried in, out, anything that's destroyed, and then our change in exergy of our system, right? And then X destroyed is our T naught S gen. Well, this one is the rate. Okay. We have reversible work, right? So that's where we took this whole section, made it work reversible, right? And then we set X destroyed equals 0. So this was not what is actually happening in our system, but this is more of a theoretical of what is that reversible work? What would that reversible work to do the same process of 1 to 2? What work reversible would we have to put in, or what work reversible would we get out if we had no irreversibilities? Right? So that's this one, where you make work equal to work reversible. We set X destroyed equals 0, and we just apply our states and the heat transfer to it. Okay, and we see what we get. If this one's showing a single stream, so one inlet, one outlet, and then this one's showing adiabatic, where this goes to 0. The other simplification we had for the heat transfer, right, was if Tk is equal to T naught, that's also 0, right? So if your boundary is big around your system, so that now the heat transfer, if you have heat transfer, your temperature, which is crossing the boundary, is T0. So that makes, there's no useful work with that, and there's no exergy. So that makes that term go to 0 also. All right, second law efficiency. So instead of just looking at energies, we're looking at the efficiency is based upon what the second law describes too. So this was a few of our simple ones with thermal efficiency, looking at the reversible version from Carnot, same with the COP. But also we could just look at it with work producing device, just comparing the useful to the reversible. Same with work consuming. And then we had there's a whole mess of equations in the book about second law efficiencies. And that was just off of this basic equation right here. Okay, what is the exergy being recovered? So that's the exergy leaving your system. What's the exergy being supplied? What's the exergy entering your system? Right, so that's what it really comes to, and that's X destroyed. So this all just comes from your exergy balance. And that's what all these equations come from that they have down here. They just set up their exergy balance for, in this case, for a turbine, and just looked at that exergy balance of what's being recovered, what's being supplied, and then some of these they simplified. So it's not just really easy to just look at it and say, oh, that was supplied, that was recovered. You actually have to do the exergy balance to see these terms of why this is the numerator, why this is the denominator. You actually have to go through and set up the exergy balance for these to see that that's what it all comes from. It's not so easy to just see just looking at it. This one's from, these right here from this method of it. These ones are showing the one with the extra instead. Okay. Same with this one's from the extra. So you can have the different methods of how to set it up with whether you're doing recovered, supplied, destroyed, supplied, right? So if we looked at this is our destroyed term, and then any of these other ones, if you're a steady state device, so this, that for energy from mass flow in and out could be recovered or supplied depending on whether you're putting exergy or useful work into a system from the mass flowing in and out, or are you recovering it? So if you're like a turbine, excuse me, for a turbine, you're putting work into the system from the mass flow because it has useful work ability to do work in that, and you're recovering it from the work on the shaft of the turbine. Okay, where a compressor is doing the opposite. You're putting work in and you're recovering it by raising the energy within the fluid properties at the exit. Okay. Or if you have a heater, you're putting exergy from heat transfer in and you're recovering it, say with this mass flow rates. So it's all on what energy or exergy is going in, what's coming out. Any questions? Chapter 8. I know that was the earliest one we covered, so if there was any things there. All right, so chapter 9, we did our closed system. So this is when we have chapter 9 is our gas power cycles, right? So this is a closed system one, which is the Otto, right? So the Otto cycle has isentropic compression, constant volume heat addition, and then isentropic expansion, and then constant volume heat rejection. How we described it with the compression ratio, so that told us about this change we have here, right? And we have available to us, we have closed system COE, which you see being applied to the heat in and the heat out there because they're constant volume processes. And then we also have isentropic equations for 1 to 2 and 3 to 4. Okay, and that's what you see here. And then setting up thermal efficiency, just our work net is our desired output, required input heat, and then rearranging it, we can do it a version with heat out and heat in. Diesel cycle. So again, closed system. We have compression ratio to help us describe 1 to 2, but then we have a new state, right? So now we have state 3 that's not at the bottom dead center, top dead center, so that's where we have our cutoff ratio that describes where state 3 is, okay? We have our COE available to us again, so that's what you're seeing here from 2 to 3. They're doing the COE right here, closed system COE. Here we have closed system COE from 4 to 1, which looks exactly like the Otto cycles, okay? And the big difference is you still have isentropic 1 to 2, but 2 to 3 is that constant pressure heat addition. So you have work and heat occurring from 2 to 3, right? Because the boundaries moving, so you're having a change in volume, so you have work, right? But you're also adding heat in this. All right, so now we have, still from chapter 9, we have the Brayton cycle. So this is our open system, still an ideal gas, right? So within this, you know, you have each of these components where you apply the open system conservation of energy to those components. Okay, so we have isentropic compression in the compressor. We have constant pressure heat addition in the heat exchanger, isentropic expansion in the turbine, and then we have constant pressure heat rejection in the last heat exchanger. So we're getting work out here, we're putting work in here, and then our net work goes outside our cycle to a generator. Okay, so then we have conservation of energy available to us, so COE, right? So this time it's open system COE. Okay, so here they did heat in, heat out. We have, describing this, because it's an open system now, we have pressure ratio, okay? Because pressures are what's being changed, right? We have our isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection. So we're at two pressures, right? So that describes the system, so that's why we have pressure ratio. And then we also have isentropic processes from 1 to 2 and 3 to 4, so through our compressor and through our turbine. Okay. And then again, thermal efficiency just applies what we get to that same equation. We can add a little bit of more accuracy to it with isentropic efficiencies for the turbine and the compressor. Okay, so we then have to deal with the isentropic value from 1 to 2 and the actual, right? So you have the isentropic versus the actual where we have to deal with. Okay, and that's where, you know, you end up over here and over here. Right? 4 actual, and this becomes 4S, 2S, and this is 2 actual. All right, so now adding some, let's see if I got more stuff there. Okay, we have the Brayton cycle with regeneration. Okay, so this is the same Brayton cycle, right? We have heat rejection over here still. They're just now recovering some of that energy that you would be exhausting to the atmosphere and moving it over to after the compressor, so you don't have as much external heat coming in. So less heat in and less heat out. So it's moving that energy inside the system. Okay, so the overall diagram looks the same as your typical Brayton, but the difference is you're just moving some of this thermal energy from 4 to 6 over to 2 to 5. Okay, so preheating it before it goes to the combustion chamber. Okay, and how we, you know, if it's 100% regenerator, then your max is equal to your actual when you're able to get to this point right here. From 2 is all the way able to go to there, 5 prime. If not, you're lower than 5 prime. So here's where it gets a little crazy. We have our, you know, with intercooling, reheating, regenerating, and you just got to walk through each component, right? Isentropic compression, intercool, compression, right? Left to right, you're adding heat. On your isentropic or TS diagram, right to left, you're removing heat, which removes entropy. Right, if you just think of this part of it, now if you're adding heat, you're adding entropy. If you're decreasing heat, decreasing entropy, and that's this part. So now we're adding thermal energy from 4 to 5, so we're going to go left to right. It's constant pressure, And then we have our combustion chamber, keep going. Isentropic through the turbine, and we have a reheater. So at constant pressure, we're adding heat. Isentropic expansion, and then we're moving heat, moving thermal energy 4 to 5, and then we have our heat rejection over here. Okay, so right to left. Okay, you just got to step through each component. Oh, so in this case, you have heat in here, right? Heat in the reheater. You have, work in for the compressor 1, work in, compressor 2, work out, okay, for turbine 1. Okay, so your network, which goes to, your external or to your generator, is now this one plus this one minus this one minus this one, right? So that would be your network, or your heat in minus your heat out. Oh, we also have a heat out here, right? All right, so here is second law analysis of the gas power system. So really, this is just chapter 8. They're just putting chapter 8 equations here and like substituting things together. So they just did x destroyed T naught S gen, and then they just put in the exergy balance inside for S gen. And now for closed system, they did it again here with heat in and heat out. So they just expanded S in and S out. So they're just re-putting in the equations from chapter 8. Here for x destroyed for an open system for steady flow component. Again, they're putting in S gen, steady state. You just have S out and S in. So they're now putting in S out and S in right here. So they're just putting in multiple equations and simplifying. One inlet, one outlet. Simplified it in this equation right here. Exergy destruction of a full cycle. So this is if you were to put, let's do a simpler one. Let's do this one, that's fine. Let's say we put our boundary around the whole system. We wanted the exergy destroyed of the whole cycle. You only have heat entering your cycle there and heat leaving there. Okay, and then a network, right? But if you're doing entropy balance to get the S gen, T naught S gen, right? If it's a full cycle, there's no work in S gen, right? It's all heat transfer. So if it's the full cycle, there's no change in entropy. So all you have is heat over temperature. So it's a nice simple, reduces to a simple equation for that S gen term from the entropy balance when you have your boundary being the full cycle. All right, and then closed system exergy, open system, or stream exergy. It's flowing in and flowing out. Chapter 10, we just now have a vapor, so we're changing phase, right? So we have each of the components are open system. So if we looked at the pump, boiler, turbine, condenser, each of them are an open system, right? So we have the COE shown here for each of those open systems. They're one inlet, one outlet, which is being shown. So it's just ends up being change in enthalpy. We also, for the pump, have this VDP, right, from the steady flow reversible work. From TS diagram, we have the vapor dome in the middle. It's still two pressures, like on the Brayton cycle, but we have changing of phase. So we have these two pressures. We have this P high, pressure low, okay? Pump, now we're adding heat in the boiler, so we at constant pressure, so we're going left to right. And then we isentropically expand in the turbine, and then we reject heat in the condenser, so we're going right to left, and then we go back to our pump, okay? The thermal efficiency equation looks the same. And then work net is either heat in minus heat out, because you put your boundary around the whole thing. All right, so you have work out, work in, Q in, Q out. We can also, again, put it in our isentropic efficiencies, right? So 1 to 2 is isentropic. 3 to 4s is isentropic, but if we want the actual, we have 4 actual, we have 2 actual, and we have to bring in our isentropic efficiencies. So this is vapor, so this is where we have to use our tables in this chapter, right? So this is our A4 to A7, okay, for water. Reheat, so adding some components for a little bit more efficiency or more work. Okay, so reheat, we just have this additional, where we're adding heat, we expand the turbine once through one turbine, add that heat, and then expand again. Okay. We have open feed water heaters and closed feed water heaters. So this is where we're pulling a fraction of the mass Y here, and the rest of that fraction of mass, so this is coming in with 1, the total mass coming in, and then Y fraction leaves here, and the rest, or 1 minus Y, leaves through that side. Okay, we're splitting up that mass. Okay, the total mass comes through the boiler. Right? Okay, so when we do the COE, the lowercase q, when we divide by that m dot 5 or 4, we just get that. But when we look at heat out, we have 1 minus Y flowing through it. So we have that as our term there, because we divide by the total mass flow rate of 4 or 5, and we end up getting 1 minus Y there. Okay. Work out of the turbine. Okay, same thing. You have 1 going from here to here. So total mass goes across that change in enthalpy, but then we have 1 minus Y going across that remaining enthalpy change. Our diagram, we have our isentropic pump. Okay, here we have 3 pressures. Okay, and you can see it in the turbine. 1, 2, 3 pressures. Okay, we have our intermediate pressure right here lines, because of the open feed water, they're all at the same pressure. We have our high pressure right here, right? We have our low pressure right here. Okay, so low pressure line, intermediate pressure line, high pressure line. Okay, isentropic. Now we have open feed water heater that takes us 3 to 4. 3 to 4 is our pump. Again, the inlets to the pumps is a quality of 0. Okay, you see that here and here. Okay, and then if we go through 4 to 5, we have our turbine that's isentropic that expands all the way to 7. We pulled some off in 6 to create 3, right? So we have 2 and 6 giving us this outlet at 3. Closed feed water heater is now, it's not basically open where they can all mix. So within here, you have 2 separate things. 7 goes to 3, and 2 is connected directly to 9. So it's basically just a heat exchanger, okay? But they call it a closed feed water heater because it's descriptive for a vapor compression cycle, or a Rankine cycle, sorry. So we have, in that case, that means it changes our pressures because of that. They're not all the same pressures going through the closed feed water heater. We have 1 pressure. We see this pump. We see here. Let's see where so we have 3 pressures, right? But if we carry it through, this is our low pressure. Here we see 1 pressure stays the same right here, so that's our intermediate pressure. This side now has all the same high pressure. all through here because there's nothing changing its pressure. This is mixing, so it's all the same pressure. We have a pump that changes the pressure. This is all the same back to here. Okay, so this raises it all the way up to the high pressure. So we still have three pressures. Okay, low goes 1 to 2. So that raises all the way up to the high. Okay, and now we have a lot of points next to each other, but 2 goes to 9, or because of the heat transfer from the other side, and then 9 mixes with 4 down here to give us 5. So 5 has got to be in between. 5 has got to be in between 9 and 4. Okay, so then 6. So we go to add heat. We go all the way to 6, and then we expand through the turbine all the way to 8. Okay, we pulled some off. You know, you have your condenser here, but we pulled some off at 7 to go through the closed feed water heater, and that dropped from 7 to 3. Right, and this is inlet to the pump. So again, it's quality of 0. Okay, and then we have a pump right here to raise its pressure to the mixing chamber's pressure. So we had it go up in pressure. We also saw a version, you know, through a closed feed water heater where we dropped the pressure. Okay, this version, you know, we could have a valve. The version we have here is taking this outlet and raising its pressure to meet up with this line at the higher pressure. There's the other version where you're dropping its pressure coming out of this to put into the condenser. Okay. I think we did an example with that where this one shows the mixing chamber raising the pressure. We did an example in class that showed the dropping in pressure. So then second law analysis of the vapor power cycles. The equations are exactly the same as what you saw for the second law analysis of the chapter 9 cycles. The difference isn't here. The difference is in how you get your properties and your specific components, because this is tables for properties, right, where you had ideal gas for the ones. So you had ideal gas law and equations for the ideal gas for properties. But otherwise, they're showing the same equations here. I'm going to pass that one. The ideal vapor compression refrigeration cycle. So this is chapter 11. So we have a simple one being shown here. So now the cycle's going counterclockwise because we're putting in work. Okay, the other ones went clockwise. So work in. The other ones went clockwise, so we got to work out that net. Okay, so in this case, we have, if we start at the inlet to the compressor, so it's saturated vapor, we compress. Okay, we have two pressures in here, so we have a high pressure and a low pressure. Okay, so we raise pressure with the compressor, and here's our high pressure, right? And then we have a low pressure. And then we take that and we put it through our condenser, so we're condensing the refrigerant, which has heat go out of our system. Okay, and then we come out of this at state 3 is a saturated liquid, so we have a quality of 0. Then we go through our isenthalpic, so H, delta H is 0, right? And then COE, say, is open system. All right, so our constant enthalpy, and then our evaporator. So we're evaporating the refrigerant because we're adding heat from a refrigerated space. Now it's just modifications. Let's see, we've got 5 minutes. So So modifications of this cascade is just putting one vapor compression refrigeration system on the other. Okay, so putting one right on top of the other, and then how it changes. Basically, we get a better COP doing that. Okay. We have the multi-stage compression refrigeration. So the big thing is in this one, it's the same refrigerant, but this one could be two different refrigerants on the top and the bottom could be different refrigerants. Here it's the same, okay? But the big thing is the flash chamber takes all the vapor this way and all the liquid that way, okay? And that's where the big one was your quality, right? The quality at 6. Quality is mass of vapor over total, which is in this case mass flow rate of 3 over the mass flow rate of 6. And then mass flow rate of 7 is just the difference between those two from conservation of mass in the flash chamber. Okay. And you can go through the problems where you have, mixing chamber, so they mix together, where now we have 6 splits to 3 and 7. Okay. Compressor. So everything here is the same states, right? Saturated liquid at 5 and 7, saturated vapor at 1. Okay. These change pressure, right? Compressor and expansion valve, those are our pressure changers. All right, gas refrigeration cycle. This is just a Brayton cycle in reverse. So instead of it going this way, it's going this way on the TS diagram. And to do that means you have a compressor from 1 to 2, heat exchanger, turbine, dropping pressure. Maxwell, so this is chapter 12, which isn't on the exam. We have Joule Thompson. This is chapter 13, which talks about gas mixtures. Okay, really what's mole fraction, mass fraction, and going from one to the other with molar mass. And partial pressures, this mole fraction right there. How to get properties. Here's chapter 14. And one of the big ones, I mentioned this before, you kind of did your homework, you had your exam, but knowing the difference between absolute or specific humidity, it's just mass of water vapor over mass of dry air, and relative humidity. Relative humidity changes with temperature. So if you're changing temperature, you're changing relative humidity. If you're changing dry bulb temperature, you're changing relative humidity. Okay. The specific humidity, if you're changing temperature, if you're just adding heat or removing heat, you're not necessarily changing specific humidity unless you cool down and hit the 100% relative humidity. Enthalpy, right, in the table has the dry air enthalpy and the water vapor inside of it. Okay, so on the psychrometric chart, it's described in per kilogram of dry air, but that kilojoules has the enthalpy from the dry air and the water vapor that's inside of it. So it's the enthalpy for the moist air, even though it's per kilogram of dry air. Dew point is if at constant pressure, that constant partial pressure of the water vapor, you cool it down until it hits the dome. Okay. Wet bulb or adiabatic saturation temperature is basically a state where you have a relative humidity of 100%. Okay. What is that temperature? General lines on a psychrometric chart you see here, which is in the psychrometric chart, shows you kind of your general lines. Also shows you, how the wet bulb, dry bulb, dew point meet up. General lines for air conditioning processes of heating, cooling, heating and humidifying, cooling and dehumidifying. Mass balance of dry air, mass balance for water. Okay, conservation of energy. That's just your open system conservation energy. They've already neglected kinetic and potential and said steady state. All right, chapter 15, we have our air to fuel ratio, so just mass of air over mass of fuel. And we use the moles times molar mass to get there. And then everything else is really just conservation of energy in the rest of this chapter, in chapter 15. It's a conservation of energy. We have enthalpy is what's different. We have the enthalpy of formation, and then we have the sensible enthalpy. And we have to basically have this difference because the enthalpy of formation already includes everything up to 25 degrees Celsius. So we have to subtract off that component when we have this enthalpy in there. So we only get what's that energy above 25 degrees Celsius from this section. All right, conservation energy, we have it with rates here, or really what we end up using is this version, which is all per kilomole of fuel, because we can always just scale it with some molar flow rate of fuel, or we know this many moles of fuel, then we get this much heat. So heat would just be units of, say in this case, kilojoules per kilomole of fuel, right? So if we know how many kilomoles of fuel, so this would be our Q, let's say Q out, we can just scale it with the moles of fuel. Or if we know a molar flow rate of fuel, we can just make that into kilowatts with the flow rate. So we look at it just per kilomole of fuel because that's more like a standardized way, and the amount of moles or the molar flow rate just scales it big or small system. Closed system just adds this minus PV. And then we have chapter 16, which we just covered on Monday, okay, where we have our equilibrium constant. So the two big versions is this one. And you saw that in the example I did early in class. This is what I set up this side. And then this is what's in your table A28, where they've already calculated the equilibrium constant, okay. So that I actually did get through all 45, and I am 3 minutes over. Any questions? Oh, the other, I know it's always a great thing to look back on that when you do the review slides too. You see how much you actually learned. The other thing I wanted to mention about the project is you hopefully saw my announcement, but make sure when you go into Canvas, you can look at your project report itself. On the report, I have the comments, not just in the feedback part where you type something. There's stuff within the report itself. You got to click in and show comments to see where I went through and saw some things. And then on the announcement I sent out yesterday too, I have a list of kind of questions and comments in general that I saw across a lot of reports. And those are kind of questions that I saw that came up with not being shown within reports, or questions I ask when I'm grading. Okay, so everyone, got the draft, you got full credit. It's not to say that's what you're going to get for the final. All the drafts I do is more to help you. So I don't have, I want people to do well in the report. So the draft is to help you, be better with your time, because if you try to do your final report the day before, what I would have saw was all the drafts of the final report, and that wouldn't have been a good thing on the grades you ended up with, just because it takes time.
Are those homework grades?
Huh? Sorry.
Are those homework grades, like the report drafts and memos?
Are those homework grades? No, they are part of the project grade.
How much?
I mean, I don't remember. I think they're each 10 points, and then your project final draft is 100 points. So you can put them together, and you get your project.
So like out of 130 or something.
Yeah. So the other part of it is that I wanted to mention is there's also, after you submit your reports, I will be sending out a peer eval. Okay, so it'll be automated from a website called Teammates. So you'll get that email through them. I set it up on their site, and then they do the automation of giving you the link to go to get your feedback. And I do this for any time I do projects. So you will review yourself and your teammates, and you can put comments about them. So then that I see, whether the group grade is what you get, or is your grade above or below the group grade based upon the feedback I get on that peer evaluation. Okay, so I don't send it out until after the final report's submitted, because sometimes people really put it together in the home stretch and start doing a lot of work on the project versus throughout the whole semester, and so then that'll help them on their team for that part of it. So I do that just because I don't necessarily like when one student doing all the work. I want a good shared grade. So if everyone's equally doing the amount of work, it'll show in the peer eval, and everyone gets the group grade. Okay. If not, someone's grade has to go down for someone's grade to go up. Okay. All right, so that's the last thing on the projects. Any other questions? I know I went way over. If not, I'm available by email. I know I'm not sure if some of them are in there. I know there's a couple project emails I got late last night, so I'll have to look at them after class today to reply back to those students that emailed me. All right, and that's it. Good luck on Monday and Godspeed. And if you have any questions on the material, the project, please let me know. Set up a Zoom or answer through email. Okay.
All right. Thank you.
All right. Have a good one.